Welcome to the new video. In the previous video, we have seen how you can change parameters in order to perform manual calibration. In this video, we're going to see automatic calibration. There are a few things that you have to check before you can perform an automatic calibration, or any calibration for that matter. The first, you have to check the default model performance. Always take a look at the default performance because it can tell you if your model has serious problems. For instance, if the peaks in the simulations are not aligning with the peaks in the observations, it might be a sign of problems in your precipitation data. Sometimes, changing the structure of the model, which includes changing whether you are using dominant or multiple HRUs and the level of simplification, will improve the default model performance. In any case, changing parameters of a model should not be used to fix problems that come as a result of bad input data or bad model structure. And you can only find out about these problems if you check the default model performance. Another important thing to check is your data. This is the observation data that you calibrate your model to. Specifically, you have to check where you have missing data and where you have available data. This helps you identify if you have enough data to perform your calibration and also later validation, and also helps you choose the periods for your simulations during calibration. That brings me to my next point. You have to split your data. Based on what you have seen when you checked your data, you have to identify a period for calibration and keep some data for validation. We can see that our calibration period is where we don't have too much missing data, and we have selected the validation period in a period where we have data. Make sure that you have enough data for all these periods. I recommend a minimum of 4 years. You can have as many years as you want, as long as your model runs fast enough. The more the data you have, the better. But due to computation problems, we always limit this to a few number of years. One last thing, you have to perform a sensitivity analysis before calibration. This helps you identify which parameters have the most impact on your results, and hence allows you to focus on those parameters instead of focusing on parameters that would not make any difference even if you calibrated them. In this video, we are going to use Ipeat Plus to do the calibration. But now, Ipeat Plus has been bundled in a tool named Gems Plus, which also includes sensitivity analysis and some evaluation. You can download Gems Plus version 1.0 from the link in the description. For me, I have already downloaded it, so I'm going to install it now. Click Next and install. Once the installation has finished, you can click Finish to exit setup. Alright. To open Gems Plus, you can click the icon on your desktop, or you can click Start and click on the recently added programs. Open. A few things before we begin. Some of you might not like the color, so you can go to UI settings and change to the color that you like. You can change it to white, and some of you to red. I like the blue, so I'm going to leave it at blue. Okay. I must mention that I have only tested this tool on the computers that have the language settings set to US English and the region settings set to US English. I had problems with the French number system because they interchange the comma and the dot symbols, and that it doesn't work. So if you have any problems running this tool, try changing your language settings and region settings to US. Alright, the first thing that you have to do is create a new project. And to create a new project, you first of all click on New Project, and then here you can browse to where you have your project. I will click the button, and then here I have Robit. This is where my model is, and scenarios, and then TxtInOut folder. So you select this TxtInOut folder and click OK. Now you can save the project. So I'll save my project on the desktop, and I will name it Robit Calibration. All right. Now I have saved it. Next time I want to open the project, I can just find it here and click, it will open. I will show you how that goes. And I open again the interface. Here it is. And then I click on it, it opens. Good. Next, I can click on this button to go to parameters. In this view, I can click on the parameter group where you have different groups. And for HRU parameters, you have, for instance, the curve number. And you can have percent change or absolute change. We're going to leave it at percent change. And in the future, I'm going to add the ability to target specific HRUs. But for now, leave it to 0 to target all HRUs. You can add another parameter, let's say ESCO. And in this case, let's change it to absolute. So this is the freedom we're giving it to add or subtract to the initial parameter. I'm going to set this to 0.01. So it can only reduce the parameter and not add anymore. If you have made a mistake, you can use this button on the right to remove the parameter that you don't want. I'm going to add one more parameter, alpha. I'm going to make it percent and then add. Okay. So in this table, you can see you have the parameter name, change type, and then the minimum change, that is the decrease that you can have from the initial parameter, and the maximum. You also have the object type to remind you what group that parameter belongs to. And here it applies to all objects in your watershed. Now you can go to observations. Click next. My observations are already prepared on the desktop. I'm going to show you the formatting of the data. The observations for flow should be formatted with date in the format of day, month, and year, and should be comma separated with flow in cubic meters per second. I'm going to open that in text editor just to show you how it looks with the comma separations. Here, day, month, year, and comma separated. All right. Now, you might be wondering, how do I know where my main outlet is? For instance, these observations are for the main outlet for Robit catchment. So you can go to map view and you find this map that you can scroll to zoom, and you can move around by just clicking on the mouse. If you click on your outlet, it will tell you the channel ID for that area, just like any other. Wherever you click, you get information for that point. But this is our outlet area, and the channel ID is 53. So I can go back to table view and then enter 53, and then I can select the observation file on my desktop, open. And here you select the observation variable, and in my case it's flow, so I leave it like that and click add. So now I have added my observation file. If I make a mistake, I can remove it like this and try again. Or if I have more observations, I can still add more of them here. Now, if you click next, then you go to calibration settings. In this view, you have different optimization functions such as NSE, R-squared, and many more. You can choose either of these, but for now, we're going to leave it at natural glyph efficiency. And here, you can choose the starting parameters between initial and random. Perturbation factor tells you how much variability you have between succeeding parameters. And the total number of years simulated, we're going to leave it at 4 years. And the start year, according to our observations, Our observations start in 1993, so we can start in 1992 and use the first year for warm-up period. And we also know that our data is at monthly time step. When we have set this, we can go to calibrate model. But in this case, we'll first of all perform a sensitivity analysis and then go to calibration. So click next. And here, there is provision to parallelize the sensitivity analysis process. So if you want it to run faster, you need to increase the number of processes. If I put 5 here, what will happen is that James Plus is going to duplicate my TxtInOut folder 5 times, and it will split the total number of parameter samples into those 5 TxtInOut folder and run them in parallel. Which means instead of running them sequentially, where it could take longer, you have almost shortened the duration of the runs by the number of processes. N is more of a seed. It defines how much number of runs you're going to end up with. If I put 1, then I'm going to just end up with 5 runs. But for sensitivity analysis, you need more than this. So I'm going to select, for the sake of demonstration, 10. This means it will launch 5 parallel processes, and each one of those is going to run 10 parameters instead of waiting for one long simulation which would have run 50 times. Okay? In the future, we'll have different sampling method, but for now, I have just put the Latin hypercube. And the sensitivity analysis is 1 factor at a time, with more options in upcoming updates. Okay? So to begin sensitivity analysis, you click on Start. It's going to write the observations. Normally, you don't need the observations, but in this case, the reference is the observations. If for some reason you want to stop and change something, you can click Stop, but this will take longer than usual because when you launch parallel processes, you have to find each process and stop it. So it takes some time, but you can stop it at any time you wish. So now it's copying the files. It duplicates the TxtInOut folder into 5. This is important to know in case you don't have enough storage on your computer. I'll speed up the process. Alright, once the sensitivity analysis has finished, you find a ranking from the most sensitive parameter to the least sensitive parameter. You can click on this button to change. At monthly time step, it shows that alpha is not sensitive. So we can go back to the parameters and remove alpha so that we don't have to calibrate it. Once you remove the parameter, you can go back to the calibrate model. Okay, next. Here it will tell you the first 1 year will be used for model warm-up. Only years from 1993 to 1995 will be compared to observations. This helps when aligning your observation data to the simulation data. However, if the data does not exist in the observation file for this period, it's going to be filled with missing data. Avoid having all missing data for the entire simulation period for the calibration. Otherwise, you will have an error. Okay, so now that we have the parameters we want to calibrate and we have already added the observations, what remains is to write files. So you click on Write Files. It will ask you, this will override any Ipeat plus files in the TxtInOut directory. Continue, you say yes. So this will write the files necessary for use with the Ipeat plus framework. When ready, you go and click Run. And then you can see the progress of the calibration. It will come here with a graph, and I will speed it a little bit. So we see that the evolution of 1 minus NSE is decreasing over time. And with each run, it goes down until it flatlines. So when it flatlines, it means there is no more improvement. If U value is below 1, less than 1, it means your Nash-Sutcliffe efficiency is positive. So around here, it's around 0.1, 0.2, all the way up to 1. Right now, we can say it's around 0.4 something. So I'm just going to stop it for now. I will not wait up until it finishes. When it finishes, this button, Run SWAT Plus with best parameters, becomes available. To demonstrate how this button works, I'm just going to run a few number of runs and then run with best parameters so that I can go to evaluation of results. Okay, I'll set it to 5. Maybe I should put it to 7. So it will run 7 times and then it will finish the calibration. And then after that, it runs the model with best parameters. All right, we see now it says calibration finished, which means it has reached the number of the runs that we specified, in this case 7. Now we can run SWAT Plus with best parameters. So I click on Run SWAT Plus with best parameters. So it will apply the best parameters first and then it will run. Okay, so now I can hide this window. And now I'm ready to evaluate my results. When I click on Evaluate Results to look at the water balance, you can click on Refresh. And this gives you all the components of the water balance, and all units are in millimeters per year. So we can already see here that this is the surface runoff is quite a huge component, and also the ET here. And this is our potential variable transpiration and lateral flow, and then here you have the return flow. And also we can see the percolation, reverb, and this is the loss out of the watershed, and this is the recharge to deep aquifer. So this is the average curve number for your watershed, and here is your precipitation. And here there are some ratios expressed as percent of precipitation, and we see based on these percentages that the surface runoff and the evapotranspiration are the biggest components. Also here you get parameter information that is giving you this water balance. In this case, this is the best parameters from the calibration of the model, and you can see the parameter and the type of change and the actual value for this Nash-Sutcliffe efficiency. So this is our best Nash-Sutcliffe efficiency after making 7 runs. You can extract the information, you can extract the flow hydrograph like in previous videos and plot it yourself, or you can recalculate the Nash-Sutcliffe efficiency again. But this is how the tool can be used to support your SWAT Plus model applications.